All right, it's time to take the journey to understand how a human memory is formed. So this part of the series is called Creating a Memory, from encoding to storage to retrieval. Now, in preparation for this lesson series, hopefully you understand some basics about the brain and neurons and working memory and plasticity and different kinds of memory, episodic and semantic, and these neurological patients, HM and Clive, and you're familiar with the hippocampus and this process of memory consolidation. In this background lesson, we also introduced two kinds of metaphors for the nature of the relationship between the hippocampus and the cortex. And we'll say the hippocampus is a printer, going to be helping to print memories in the cortex, or the hippocampus is a learner itself and then a teacher. And that teaching process is what we call consolidation. We'll see these metaphors in the upcoming lesson here. So we're going to follow the path of a memory. And to do a quick sort of preview of what we're going to find, let's remind ourselves of what we learned about in the previous lesson, that there are 3 steps to make and use a memory. And here we have a brain here, and we see some of the neurons. Some are dark, some are bright, white here. And the idea is maybe the white ones are currently being activated by whatever the brain is processing at the moment. And here we see magnification of that. The white neurons would be activated. So we have a particular set of neurons responding, and others are not responding in that scene. Well, the first step is encoding. Encoding, a set of neurons respond to the learning event depending on the qualities of the learning event. So again, it's important to think about that it's only a set of neurons. A certain unique pattern of neurons will respond to any particular learning event. And this will be happening all over in those brain areas that are processing the learning event. So we've got a set of activated neurons. And then we'll have the storage phase. A subset of activated neurons will take part in making a memory of the event. And what that involves is that these neurons grow stronger synapses with each other, forming a memory trace for the event. So there was a certain set of neurons that responded to the learning event, and then a subset of them are going to actually grow stronger connections with each other. And that would be the formation of a memory trace in that region of the brain. So the result then would be neurons with strengthened synapses form a network of neurons that represent the stimuli in the learning event. So we've got a memory trace in the sense that we've now strengthened a connection among a network of neurons that were activated during the learning event. Now for retrieval, the idea is a retrieval cue, reactivates the network of neurons that enjoyed strengthened synapses as a result of the learning event. The stored information is retrieved. So the key concept here is that when we retrieve a memory, we're trying to reactivate those same neurons that responded and grew stronger connections with each other during the original learning event. So you can think of it this way. When we retrieve a memory, we are trying to recreate the brain state that occurred during encoding and storage. And if we're successful, we will enjoy a retrieved memory. Okay, so let's follow the journey then, or we'll take a journey and follow the creation of a memory and its retrieval. And the situation again will be the event of observing the total solar eclipse in La Serena, Chile in 2019. Here's what it looked like that day. This is time-lapse photography, so a camera taking a bunch of pictures and then all strung together and played as a video. But of course there were sounds in the environment as well. Let's take a listen. These were the moments right before a total eclipse.
Here it goes. Wow. My God, look at that. Look at that. Unbelievable. It is unbelievable. That is the most beautiful thing I've ever seen.
All right, so while the picture sort of makes it look like myself and my wife are the only two on the beach that day, there were thousands of other people enjoying this spectacle. So what was happening in the brain? Well, the different sensory areas of the brain were detecting and registering the sensory qualities of the experience. So the feel of the sand on the beach was activating touch areas of the brain. Of course, the sight of the solar eclipse was activating visual cortex, and the sounds in the environment were activating auditory cortex. Now we're going to use the little paper here with the pen here, and this is going to be our icon for a memory being formed of the event. And as we already see here, scientists think that we store the memory for an event like this in distributed areas. So what the scene looked like, the memory for that will be stored in visual areas. What the scene sounded like will be stored in auditory areas, etc. Now, to get a handle, get a feel for what's happening in the brain in these different locations as the brain processes this scene, what we're calling encoding, the brain is processing the information from the environment. Let's use this video to sort of give ourselves an intuitive feel for what's going on. Now, this is the picture of the surface of an animal's brain. And in a moment, I'm going to play this video, and you're going to see something unusual. Now, typical neurons, when they generate electrical signals, they do not emit light. However, scientists can insert genes, DNA, from other species that will give neurons the ability to emit light when they generate electrical signals. So over here in this film, which you've already seen before, if I play the video, these little flashing lights are neurons that are emitting light as they generate electrical signals. So this is an animal that is awake and observing some scene, and we can think this is what's going on in our brains when we're awake and processing information. So we've got a certain pattern of neurons that are being activated by whatever stimulus is in the environment. Here we see the similar scene on the left here, but now we're going to magnify the box over here will be shown on the right. And again, you'll notice flashing lights. Those are neurons that have been genetically engineered to emit light when they generate electrical signals. The big tubes here are blood vessels. In fact, you might even see some blood cells moving through the blood vessels. So if we imagine then that this bit of tissue is in the visual cortex, then the particular details of that visual scene are going to activate a certain pattern of these neurons. If I were someplace else in the world looking at something different, it would be a different pattern of activity, right? So the activated neurons in the visual area here are specific to the specific kind of visual stimulus coming into my brain. And likewise for the auditory cortex and the touch cortex. So I've put this little picture here to remind us that in the brain at that location, we're going to have a certain pattern of activity in the cells at that location that represents the feel of the sand. The pattern down here in the visual cortex represents the sight of the event. And the pattern of activity in the auditory cortex represents the particular acoustic qualities of the scene, of the learning event. And now we're going to introduce yet another icon. We're going to put the little red marks around these areas of the brain to indicate that that part of the brain is currently activated. So this is the encoding stage of creating a memory. Our brain is processing the sensory and perceptual qualities of the learning event. Now we also have learned about the working memory system. We're going to put we've used boxes in the past, but here's a little cloud here represents these systems in the brain that can hold information over the time course of seconds. So this is our working memory system. Well, our brain is processing the solar eclipse scene, and then those areas of the brain will send information up to the working memory system. So we're sort of loading up the sensory qualities of the experience. So the back of the brain has extensive connections with the front of the brain, and one of those important kinds of connections is the ability then for whatever it is that we're feeling, seeing, and hearing to be loaded up into the working memory system, and we will enjoy a conscious experience of the entire solar eclipse scene. But activation of neurons is not enough to make a memory of the episode. The brain must change in a lasting way. And that's where the hippocampus will come in. a critical structure in the formation of a long-lasting memory for this event. So now we're moving on to the storage phase of this memory process. So encoding, the brain is responding to the event, and the storage phase will involve the cortical areas that were just activated. They also, in addition to sending information to the working memory system, they also send information down into the hippocampus. So we have convergence of these different sensory qualities down into the hippocampus. Now, in the hippocampus, then, there are hippocampal neurons, just a set of them, not all of them, but just some particular pattern of hippocampal neuron activation. And the idea is that the particular properties of the sound of the environment will activate a certain set of hippocampal neurons. The particular quality of the feel of the sand on our feet will activate yet a different set of hippocampal neurons. And the particular quality of what the scene looked like will activate yet another set of hippocampal neurons. So now something really important is going to happen in the hippocampus as a result of this activation by these cortical areas. The simultaneously activated hippocampal neurons are going to strengthen their connections with each other. So in other words, this set of hippocampal neurons now becomes a memory trace, in a sense, of the event. The sensory qualities of the learning experience are linked together in the hippocampus because the hippocampal neurons that were activated are now increasing the strengths of connections with each other. So the pattern of the hippocampal neuron activation here represents the pattern of activity in the cortex. So the hippocampus has made a fast memory, you might say, of the cortical activity. Now, exactly what do we mean as strengthening connections with each other? Well, here we'll use our icon again. What we mean here is the strength of the synapse between hippocampal neurons has increased. So neurons, including hippocampal neurons, are living cells, and they can respond to stimulation by strengthening these synapses between these neurons. All right, so we'll also define the term memory trace. So a memory trace is the biological change that occurred in the brain that represents the acquired information. So at this stage then, the memory trace includes the changes that happened in the hippocampus among those activated hippocampal neurons, but as well changes in synapse strengths up here in the cortex in these distributed areas. So we have a distributed memory trace for this learning event at this time. And we will we'll explain why the ink down here is more robust. It's brighter down here than in the cortex. That'll be an important feature coming up in the next part. But let's just pause to reflect that the ability of neurons to change synapse strength, what we call plasticity, this is the key to learning and memory. When activated neurons grow stronger connections amongst themselves, a memory trace of the event has formed. In a film that we saw in class called Memory Hackers, Eric Kandel and his team were showing us sort of the development of a memory sort of right before our eyes as they were stimulating neurons in a petri dish. The red branching structure would be the dendrites of a neuron, and the green fluorescent structures here would be the axons and the axon terminals making synapses on the target neuron, the red neuron here. So I'll play the video, and you can see there's going to be a growth process. The axons are going to be growing, and new terminals are going to be making connections, new synapses with the target neuron, the red neuron here. And this is the what we're witnessing then is the formation of a memory, in a sense. As a result of this learning experience, these brain cells are growing more and stronger connections with each other. Okay, so think of this process, and let's return to the state of the brain at this time. We have had synapse growth in the cortex in the population of cells that were uniquely activated by the sight of the scene and the feel of the scene and the sound of the scene, and we've got synapse growth and strengthening amongst hippocampal neurons. And again, that pattern of activity in the hippocampus is representing the pattern of activity in the cortex. So we have a memory trace of the event at this stage. We're in the storage stage. In the next lesson, then, we'll see what happens next.